Yeah, let's spend just a couple minutes reviewing the concepts that we did on Friday, guys. We started off on Friday by defining a domain, a magnetic domain. Who remembers the basic definition for a magnetic domain? You guys don't need to give me all that details about the spinning electrons and stuff like that, right? Just the basic idea of a magnetic domain. It's a tiny little, yeah, it's a tiny little region, a tiny little microscopic region inside, what's that term we talked about yesterday? Inside a ferromagnetic material, right? It's inside a ferromagnetic material. And we represent them by arrows. Now, obviously, if we look at it under a microscope, we're not going to see these tiny little arrows inside this. We're simply representing these more complicated things by arrows. Now, if these arrows are pointing in the same direction, we have a magnet. If they're not pointing in the same direction, we simply have a ferromagnetic material. What's the definition for ferromagnetic? It's all well and good to say it's these tiny little regions inside a ferromagnetic material, but if we don't know what ferromagnetic means, then that definition for domain doesn't mean a whole lot to us either. Patrick? Yeah, it's a material that can become magnetized. Give me an example of a ferromagnetic material, probably the most common one. Yeah, steel's a great one because it's an alloy of iron, right? And iron is naturally ferromagnetic. Now, if we have a ferromagnetic material, just a whatever random ferromagnetic material, then we're going to have these domains, but they're going to be pointing more or less in random directions. In order for it to become a magnet, to have a magnetic effect, then we need to align these domains, get them pointing more or less in the same direction. What's one of the ways that we can use in order to align these domains in the same direction? Yep. Yeah, bring another magnet nearby. Bring another magnet nearby it. Even if you touch it or rub it against it, that's even better. But even if you bring it nearby, you're going to cause the domains in this non-magnetized ferromagnetic material to start aligning in the direction of the domains of this magnet that we brought nearby. So these domains, although they don't necessarily point all in exactly the same direction, we get a net effect of these domains pointing more or less in the same direction. All right, so now it's become a magnet. It's a soft magnet, a temporary magnet, but a magnet nonetheless, at least for the time being. What's the polarity of this? Which end is this, the left side? Is that north or south? That's south. The domains are defined as pointing from south to north. We talked about what would happen yesterday if you cut that magnet in half. We're going to have two magnets, not a north magnet and a south magnet, but rather we're going to have just two regular magnets, each with a south pole and a north pole. Okay, just looking like that. Now, if these two magnets that we just cut in half, coming from one magnet that we just cut in half, are close to each other, then we're going to find that these two magnets are going to attract each other because, of course, we know that north attracts south. What's the other way that we could align the domains in that ferromagnetic material if those domains were scrambled again? Think of the junkyard, right? Yeah, electricity, right? If we don't apply electricity through this ferromagnetic material, we don't connect an electrical connection to this material or use a wire to cause electrons to go through this ferromagnetic material. We just wrap an insulated wire around the ferromagnetic material. There's no electrons moving through it. Okay, it's just the moving electrons through the wire produce a magnetic field, and that magnetic field causes the domains that are inside this ferromagnetic material to become aligned. Right? We talked about 3 laws of magnetism. What were those 3 laws of magnetism? The first 2 were really, really easy. First one was, yeah, like poles repel each other. Just like charges repel each other. We're not talking about charges now, though, so be careful. Okay, we're talking about a north pole and a north pole, or a south pole and a south pole. What's the next one? The next easy one. Yep. Good. Unlike poles attract. North attracts south, just like positive attracts negative. Now, we're not talking about positive and negative here. We're talking about north and south, but it's the same kind of idea. Okay, so unlike charges or opposite charges attract each other. And that third law of electricity said that charged objects attract neutral objects. The third law of magnetism says Magnetized objects, or in other words, magnets, okay, either a north pole or a south pole, attracts non-magnetized ferromagnetic materials. It's not enough just to say that magnets attract non-magnetized material. Okay? Give me a situation where a magnet does not attract a non-magnetized material. Josh? Yeah, a piece of paper, right? Okay, or a piece of wood, or a piece of glass, or a piece of plastic. Right? It has to be a non-magnetized ferromagnetic material. Why? Why does it have to be a ferromagnetic material? Why can't you just have a magnet attracting that piece of paper? We know it doesn't happen, right? Okay, we know that a magnet, probably in grade 6 or earlier, you knew intuitively that a magnet wouldn't attract a piece of paper. But why doesn't it? Why does that piece of paper have to be replaced by something that's ferromagnetic? What's the process whereby that magnet that has domains pointing in the same direction, what's the process whereby it attracts this non-magnetized ferromagnetic material? Yep. Yeah, exactly. The magnet induces the domains, and induces is the perfect word. Okay, induction. The domains inside this non-magnetized ferromagnetic material to temporarily, at least, point in the same direction as the domains in the permanent magnet here. So this is a permanent magnet with a south pole and a north pole. Temporarily, this table leg or whatever it is develops a polarity with the side that's closest to this guy that's causing it to become a temporary magnet, opposite poles. And we know that opposite poles attract. So in the end, magnets attract non-magnetized ferromagnetic materials essentially because north attracts south, and south attracts north. Right, Mandy? All right, we talked about magnetic fields as well, and the direction of magnetic field as well as the shape of magnetic field. Okay, if I draw a simple bar magnet, okay, one simple bar magnet, then the magnetic field would look something like this. Okay, I'm going to draw in the direction, and I want you to tell me what the polarity of that magnet is. Okay, that's one way that question could be asked on a test. Okay, here's the diagram. It's a correct diagram with the field lines pointing in one direction. Tell me what the polarity of that magnet is. Which end is north and which end is south? North is where? North is on the right-hand side. Is that right? Didn't we say just a second ago that domains point from south to north? Yeah. Domains are essentially the magnetic field inside the magnet. And the magnetic field inside the magnet will point from south to north. But we're usually talking about the magnetic field not inside, but outside the magnet. And that's going to be from north to south. Okay, if we continue this loop on, then you would see that that magnetic field inside would point from south to north. But when we define the direction of the magnetic field as being from north to south, we mean outside of the magnet. Okay, let me draw another diagram here. Here's two magnets. Magnetic field looks something like this. What do you know about the polarity of these magnets? Let me ask you this question. What do you know for sure about the polarity of these magnets? Okay, what is conclusive based on the diagram that you see there? Anya, is your hand up there? Good. That they're the same poles. Do we know what poles they are? Sorry? North poles? Could be. Do we know conclusively that they're north poles? No. We know conclusively that they're like poles, right? Your first answer. We don't know conclusively what like poles they are, north and north or south and south. How do we know, Anya, by the way, that they're both like poles? Yeah, they're acting like two positives or two negatives, right? The fields don't join up. The fields repel each other. So they've got to be like poles. Now, why don't we know conclusively that they're both north or both south? We don't know which way the field is pointing, right? Okay. If I draw the field going like this, okay, what does that tell you about the polarity? This one's going to be north, and of course this one's going to be north as well because they've got to be like poles, south and south, at this end. All right, one more. Okay, you know what the shape is going to look like here. I'm going to label this one a south pole. Okay, I want you to label for me this one. That one's easy, right? This one's going to be a north pole. What about this one? This one's going to be a south. What about this one? North. What about the direction of the magnetic field right here, right or left? It's going to be to the left, Alan, because it goes from north to south. Good. What about the magnetic field this way? Left to right or right to left? It's going to the left. Yeah, it goes from north to south again. Okay, what about right here? Magnetic field is going to point towards the right. Does that make sense, guys? Okay, so we asked that question, same question basically as we showed you yesterday, but we asked it in a slightly different way. Okay, you're going to see this. You're going to see this on your next unit test. I promise. You're going to see this on your next unit test. It may be asked like I asked it yesterday, right? Just basically, you don't have to draw the diagram, but basically recognize which diagram is correct. Or, okay, you may be given something like we talked about today where you're given a few blanks and you have to fill in the blanks. What's the polarity of this magnet, or what's the direction of the magnetic field? We talked about some relative strengths yesterday. And again, I told you not to write down this table. You didn't need to know, you didn't need to memorize the relative strengths. But I wanted some perspective. The big one that I wanted you to kind of take away from this was the Earth's magnetic field compared to other magnetic fields like bar magnets, okay, or even an MRI. Okay, the Earth's magnetic field, okay, is 10 to the minus 5 Tesla. What's the symbol, by the way, for magnetic field? If Tesla is the unit, the symbol is, yeah, it's a capital B with an arrow over it, meaning that it's a vector field, right? The magnetic field strength of the Earth is about 10 to the minus 5 Tesla, although it varies depending upon where you are on Earth. And it's actually decreasing. It's decreased quite dramatically, actually, over the last 100 or 200 years. In fact, so much so that some scientists think we may actually be in the process of a reversal, that the magnetic field may actually be in the process of reversing right now. It's happened, geologic records show us that it's happened on average about every 250,000 years, that the magnetic field on the Earth has reversed. North has become south and south has become north. But the last time it's happened has been about 750,000 years ago. So we're about 500,000 years overdue. And the Earth's magnetic field has decreased in strength dramatically over the last couple hundred years. So again, there's some thought out there, some real thought out there that we may be in that process right now of it reversing. And if it does reverse, it's not necessarily a process that takes 10,000 years. It could happen literally over the next 100 or 200 years. So within the lifetimes of our kids or grandkids, which opens up a whole new bucket of problems if the Earth's magnetic field reverses. Right now, it's about 10 to the minus 5 Tesla. It could get smaller within your lifetime. It could get 10 to the minus 6 or so within your lifetime. Bar magnet, about 1,000 times stronger. Okay, don't remember the numbers. Just remember that a bar magnet is quite a bit stronger than the Earth's magnetic field. Okay, how much stronger? It doesn't matter. Okay, it's quite a bit stronger. An MRI machine, well, that's a lot stronger still. Okay, an MRI machine is close to, pretty close to as strong of a magnet that human beings have ever made. Yep, go ahead. The question was, would we feel it if the Earth's magnetic field reversed? You wouldn't feel the Earth's magnetic field disappearing directly, but indirectly you definitely would. If it did reverse, what would likely happen is that it would decrease to a strength of 0 first, and then it would start increasing in the opposite direction. Now, if it goes in the opposite direction, it creates a whole bunch of issues with navigation. Right? Compasses are pointing the wrong way. Okay. Some animals use kind of a compass within their bodies, kind of a magnetic effect within their bodies to navigate. That's how birds fly south, right? That's how birds know to go south in the wintertime. So that might be an issue. What else does it do? Well, as it decreases to zero, the Earth's magnetic field as it stands right now protects us from charged particles coming from space. Sometimes you hear on the news, there's extra sunspot activity going on this week. And you guys ever heard that? Watch out for the northern lights. Have a look for the northern lights every night this week because there's extra sunspot activity. Well, the reason that we see more northern lights when there's extra sunspot activity is because these charged particles coming from the sun, they enter Earth's magnetic field and they get deflected by the Earth's magnetic field. So the Earth's magnetic field protects us from these charged particles, but it also provides this northern lights show. There's a little bit more to the northern lights than that, but that's essentially the basics behind how it happens. Not only would we not see the northern lights if the Earth's magnetic field was zero, but we also wouldn't have that extra layer of protection from charged particles coming from the sun, right? They would come straight in to the Earth and hit us. Okay, and that would cause all kinds of issues, right? When we get bombarded by charged particles, it creates, ionizing issues and higher incidence of cancer and all kinds of things like that. Not to, create this mass hysteria, because in the end, the Earth's atmosphere still would protect us. It's not like we'd be completely open to these charged particles, but we'd just be more open to these charged particles than we are right now. So all kinds of issues with that, right? Would we feel it directly? No, because we don't feel a magnetic field, right? But would it create all kinds of implications for our lives? Yes, it would. We compared gravitational with electric with magnetic field yesterday, and of course the source. Right, that's all old stuff, right? The source is a mass. The source is a charge. The source is a magnet. And of course, with gravitational field, that's the only one that has to be attractive. The other ones could be attractive or repulsive. And then where we ended off yesterday, and I know this is the thing that you took home with you and bothered you all night, the fact that Santa Claus does not live in the North Pole, rather Santa Claus lives in the South Pole. In the end, that comes from the way that we define the direction of the magnetic field, right? We define it as the way that a compass points when placed in the field. Well, which way does a compass point, at least right now? Which way does a compass point? This way, towards northern Canada. But the problem is we define the direction of the magnetic field as well as being from north to south. So this has to be north and this has to be south. But we said yesterday, it doesn't really matter. Okay, if we're all calling this north, and we do, okay, for the most part we do. When we're navigating, when we're going to Calgary, we're heading north to Calgary. Well, not really. We're heading, magnetically at least, we're heading south to Calgary. Okay, but if we're all calling it north, it doesn't matter whether we're calling it north or calling it south or calling it, Steve. Yes, doesn't matter what we call it as long as we're all on the same page, the same frame of reference, right? All right, let's go a little bit further here today. So let's say that you're alive a couple hundred years ago and you're looking for a treasure and you've got I'm kind of taking liberties with how the story actually happened here. Okay, I don't think that this guy that we're talking about, Hans Christian Oersted, was actually looking for treasure, but let's pretend he was. Okay, he's looking for this treasure. He's got this compass that's lying on a map here as he's looking around and trying to find the treasure, and the compass is pointing this way, and then he flips on some kind of switch that that allows electricity to flow through a wire. Okay, and I'm not sure what he's powering. Okay, some kind of rudimentary electrical device. Okay, and all of a sudden the compass needle starts pointing in some other direction. He's like, well, wait a second, what's going on here? The compass needle is supposed to point towards the north or towards magnetic south. Why is it pointing in this other direction right now? Well, then he flips the switch off, and then the compass needle goes right back to where it was, right back to where he predicted that it should be going, right? Towards Calgary. Well, then he flips the switch on again, and the compass needle points back in the other direction. Flips it off, points towards Calgary again. Flips it on, flips it off, flips it on, flips it off. Every time he does it, he finds that the magnetic field, he finds that the compass needle changes direction. Well, there's only one conclusion he can draw from that. If the Earth's magnetic field is causing the compass to point this way, where there's no electric current present, but when there is an electric current present, the compass needle always points this way, then the compass needle must be creating, the wire with the current going through it must be creating a magnetic field like the Earth's magnetic field. In fact, a stronger magnetic field, because it's affecting it more than the Earth's magnetic field is affecting it now. The conclusion that he drew from this was electric current generates magnetic field. It's as simple as that. An electric current generates a magnetic field. Oersted, I believe, discovered this 1819, almost 200 years ago, by accident. He gets which is the way that a lot of scientific discoveries have been made throughout history, is by accident. He's got a compass near an electric current, and the compass is deflected by the electric current, or at least by the magnetic field that's generated by the electric current. You keep repeating this, there's only so many times that you can do it before you draw the conclusion that it must have been the electric current, bless you, that it must have been the electric current that caused that magnetic field, which would cause the compass to be deflected in a certain direction. Of course, when we talk about electric currents, what are electric currents? Moving charges. So it's not the electric current per se that generates the magnetic field, it's the moving charges that generate the electric current. So you can have an electric current in a wire, but you can also have an alpha particle flying through the air. Both would generate a magnetic field, because in the end, they're pretty much the same thing. Well, what about the shape of the magnetic field? This is a little bit more confusing than it was with simple bar magnet, because now we have an electric current that's physically moving. Something that's moving is causing the magnetic field, as opposed to something that's stationary, like the bar magnet. The shape of the magnetic field will always be circular. It will always be circular. So there's going to be concentric rings of a magnetic field that surround this wire that generates this magnetic field. Okay, before we look at the direction, and before I draw a couple diagrams of the shape of the magnetic field, I want to define a new symbol for you. If I draw this, it means something's pointing to the right. If I draw this, it means something's pointing to the left, down, up, right? Those are easy ones. Those are easy symbols to show direction. But if I want something to be going into the page, right, away from you guys into the page, how do I represent that? Or if I have it going out of the page, how do I represent that? A dot in both cases? Well, two of you have heard this story already, but I'll tell it again. And for those of you who haven't heard it already, when I was 4 or 5 years old, I don't remember exactly how old I was. I'm playing in my neighbor's across the street in his basement. We used to play down there all the time. They had a pool table down there and a couple different rooms in there with cool stuff. And beside the pool table was a dartboard. He was a couple years older than I was. I remember one day we're over there playing darts, the two of us, and we're little kids playing darts, completely unsupervised, throwing darts at this dartboard. When you're 4 years old or 5 years old, you're not very good at hitting the dartboard, but when you do hit the dartboard, the darts don't usually go in the dartboard. So they hit it, like this, and then they fall off, whatever. Okay. And I don't remember if I ever even put one in the dartboard or not, but I do remember very clearly one day picking up the darts that were on the floor beside the dartboard, because I didn't have any darts on the dartboard that time, standing up, and then all of a sudden getting a dart in the back, and literally sticking in my back. So my friend, who was a couple years older than I am, threw a dart, missed the dartboard, managed to get it to stick in, but not stick in the dartboard, rather stick in my back. So I got stabbed by a dart when I was 4 or 5 years old. It hurt. I may have even cried a little bit. I'm not sure. Perhaps. Yeah, that part's a little fuzzy. I don't really remember that for sure. I may have cried a little bit. The point of that story is this, okay? I didn't even see the dart coming, right? Because obviously I'm standing facing the other way. But you can visualize the dart coming. You can see it in your mind coming towards you. When you see the dart coming towards you, you see the tip of that dart. Okay, you see this. When you see that dart going away from you, okay, which is the way that you want to see a dart going away from you, looks more like this, right? With the fins of the dart. Okay, so you're seeing the head of the dart, the point of the dart coming towards you. Right here, you're seeing the fins of the dart going away from you. So this is going to mean for us anything, okay, that's coming towards us. This is going to mean anything that's going away from us. Just like this means to the right and this means to the left. So this dot right now is going to mean an electric current coming towards us. So electrons are moving towards us right now. That magnetic field will look like this. There's a circle around that wire. There's another circle around that wire. There's another circle around that wire. Concentric circles, circles that are around other circles. What do you notice about the spacing of those circles? Pardon me? Pretty even? Not supposed to be, but that's... I didn't draw it very well because they're not supposed to be even. We got a little space here, a bigger space. Okay, the next one might be way over here. The space keeps getting bigger. What does that tell us about the strength of the magnetic field the further away from the wire that you get? It's weaker, right? And that should make sense. If it's the wire and the current in the wire that's causing the magnetic field, then the further you get away from what's causing it, the weaker the field is going to be. Okay, we get the same shape over here with this magnetic field that's going into the page as well. Now, what about direction? We have a rule that helps us with the direction here. We call it the wire grasp rule. It says, take your left hand. If it's a negative particle, that is. If it's a positive particle, take your right hand. Okay? I want everybody to do this right now. Okay, everybody do this right now. Okay, drop the pens right now. Okay, put your left hand in. Pull your left hand out. Put your right hand in. Now, shake it all about. Now, no, never mind. You're going to use your left hand here because it's a negative particle. Okay, it's electrons that are coming out of the page. I want you to stick your thumb, your left thumb, towards the back of the room, right? The way the electrons are moving right now out of this page towards the back of the room. Take your left thumb, stick it towards the back of the room. Everybody do that right now. Your left hand, thumb towards the back of the room. Then I want you to clench your fist. Now, you don't have to clench it tightly like this, but just bend your fingers a little bit, the way they naturally bend, okay? So this is the wire that's going towards the back of the room, this pen is. Okay, I'm sticking my thumb in the direction of the current, which is towards the back of the room, and I'm clenching my fist a little bit, okay, a lot, doesn't really matter. Okay? In the end, my fingers, no matter how much I clench them, my fingers, well, right here they're pointing down, right here they're pointing to the left, but in the end, any way you look at it, my fingers are going clockwise. So the magnetic field going around this would be clockwise. Does that make sense? So I put my hand like this, okay, my fingers seem to be pointing to the right. I put my hand like this, my fingers seem to be pointing to the left. But both are correct because it's a clockwise magnetic field. Does that make sense? Let's draw this one. Here we've got negative particles going into the page. So this time, we're going to stick our thumb, our left thumb, everybody do this please, towards the front of the room. Left thumb because it's negative particles. If it was an alpha particle, we'd use our right hand. Thumb into the page. Fingers go, doesn't really matter where you put your fingers. Clench them, they're going to go, which way are they going? Counterclockwise. So here they're going up, here they're going to the left, here they're going down. But the net effect of that is counterclockwise, right? All right. we'll leave it at there for today. Remember, guys, we have a quiz on Monday, not on this stuff, but on the stuff that we reviewed earlier. You have an assignment due on when? Wednesday? Wednesday? Wednesday?
Thursday.
And you have a unit test on momentum on Friday.